new developments we have faced in the past few years, and give you also some idea about how we can use these developments in the techniques. And we have heard a lot about new sources, new detectors. We have seen very nice examples already, and this applies as well into the field of planetary sciences, about everything related to the knowledge about the interior of our planets, and even going beyond our solar system into the field of these exoplanets that are coming up more and more. So it's very fashionable nowadays just to do investigations in various systems, just to investigate the possibilities of the composition of this kind of exoplanets. And I decided just to give you half of this talk some idea of an overview about what is the newest developments, and then finally showing on 2 examples how we can really do this kind of experiments and what kind of results you can get. And you will see we are a little bit back to the time like good old Lowy was, as you have shown. If somebody will show me nowadays such an image, I will, as student, I will say, go back and do the experiment again. And I mean, 100 years ago, he got the Nobel Prize for it. So that's unfair, I would say. But we have learned a lot about this. So I give you some idea about what I will talk in this next 60 to 90 minutes, maybe not that long. First of all, I will spend a few words in order to explain what is extreme conditions, because we have a different understanding maybe for this. I always give some idea about, even for a sugar, a droplet of water can be already pretty extreme, but this is not what we are meaning here. Then I will try to give you some idea about what is the newest techniques that we are using, or what are the kind of materials or any changes that had given us progress in the past few years. Based on what you have seen on the diamond anvil cell in my first lecture, I will just show you now a little bit what kind of modifications we can do just to go a little bit further. And then I give you 2 examples. First of all, in the field of carbonates, on calcium carbonate, where you might think everything has been investigated, even at lower pressures. There's still some interesting new structures coming up, and I will show you here results of measurements using a so-called dynamic compression instrument, so a dynamic diamond anvil cell. And then finally, as you have seen in the very first slide, some idea about CO2, a simple molecular compound that is existing here as well in this room as we breathe it out, but we can solidify it. If we just make it compact and take pressure, then we are able just to get it as a solid. And I will tell you a few new findings about what we have found out about the role of CO2, maybe at conditions that are relevant to the Earth's mantle. So, extreme conditions in planetary sciences. So, I was thinking, what kind of examples can I choose? And it's on this place, of course, what else than just showing you the very low temperatures. Although it's not exactly this place here, it is it's a pole of coldness in Russia. What's it called? It's a little bit far away from here, I guess. But it is one of the places where there is extreme conditions, basically. Okay, in the morning it was also pretty good, but it was only half the temperature. So, I mean, so you see, it's relative. Yeah. So what is extreme? If you look up in one of Wikipedia, whatever, you will find it is something that exceeds the ordinary, basically. So it's not something that you are used to. or that you're expecting. So something that is beyond a scale where you think it ends at some point, then you really, if you're going beyond this, then it is something that comes into this regime of being extreme. So these are all different definitions that you can find up if you look for a kind of a definition of extreme conditions, basically, or X for the word extreme. And if we just go now to where we want to apply it to, basically going to the physical parameters that we can vary, you see you get extraordinary high or even low ranges, like the temperature we just have seen. And this is just one of parameters out of the parameters that you can vary in a way. We can even add a lot of other parameters that I will not talk about, which is definitely also some field that immediately goes into the astrophysics. But we will stick on temperature and pressure or stress variations or mechanical loads. But you can see there is also gravity that is possible to get extreme, or radiation, which can really be extreme for a material. Any of electromagnetic fields, or even changes in whatever in the chemical sense you're doing, like having something special acid or special alkaline, and also then if it's exposing your material to some reactive media, and that's as simple like water and dissolving sugar in it, is already some extreme. So you get now maybe a little bit a better idea of what kind of extreme conditions we have. And just coming back to what we had just have seen with the temperature minus 67.8, not here fortunately, yeah, is at least the lowest temperature, the most extreme temperature that I think has been recorded for Russia. On the other hand, I think it's Death Valley in US, but also in Libya is a place which is close to the other side, plus almost 60 degrees. It's 56.7, that's the accepted world record of the highest temperature. But the lowest temperature, we just looked it up recently when we had dinner, is actually on the South Pole. It was minus 89.2. So you see, these are really extreme temperature conditions. But as you see here, the planet Earth, this is maybe not everything, and I've shown you the slide before, 3 days before. So you see here the temperatures of the Earth are, if you go inside, it's getting much, much higher temperatures. Now we basically end up in a temperature range somewhere between 5,000 and 6,000 Kelvin. That's what we can assume from the knowledge of our best models that we have established over the past few years. That is the temperature that you can expect at the center of the Earth, and at the same time having 3.64 million atmospheres, the pressure there. This is pretty well established because determining in the pressure is much easier than the temperature. For the temperature, there's a much higher uncertainty. On that, you can see on the, oh, that's the pointer here. You can see on this side here, you see even further for the Earth's core, the outer Earth core and the lower mantle, which is some interface and a discontinuity for whether the chemistry of the planet is changing dramatically. We have the metal core and we have the oxygen-based mantle. Here we have a pressure of about 1.35 million bars. So that's later the regime where we will talk about the CO2, what's going on there. So we have seen this as well a few days ago. This is just a reminder, just to show you again this distribution. We have also got some idea about what kind of techniques we can use just to approach it, and that we are able basically with large volume presses, with diamond anvil press, but also then in combination with laser heating, just to approach all these conditions that are relevant to our planet basically. But it's not good enough maybe for all the other planets. As you can see, just for an example, comparing the Earth with these conditions that we just have seen, to Jupiter, the largest planet, the gas giant planet in our solar system, you see it's a much higher temperature, and we are talking in this case about 100 megabars that are supposed to be at the center of the Earth. So it's just more, it's much more extreme, and this is the planet where we assume at the moment that we have metallic hydrogen in the core, basically. And basically why we are doing this is just we are expanding our view, getting outside of the solar system. And so the exoplanets are at the moment very fashionable and then in the focus of a lot of investigations in planetary sciences, and we can only place here a lot of question marks because we have no idea yet. We're just starting to get some idea about this. So what are now the kind of advances of the techniques that we have had in the past few years? So I need not to explain you all the details of the diamond anvil cell because we have seen this. I was showing you that you can use 2 diamonds in a special cut, and you will see it's not only the standard brilliant cut. In a few minutes you will see we have also alternatives that can give you the possibility just to be used as an anvil material to get the load onto your sample. The sample usually can be anything, basically, either polycrystalline but also single crystalline. We have to take care that it should be embedded in some medium that is acting in a hydrostatic way in order to get a good pressure distribution. And that's one of the challenges that the experimentalist has to deal with. And if you go to very extreme conditions, you don't have many materials for choice for this. So you end up with the noble gases, and the noble gases, especially neon and helium, are those which have the latest crystallization points. That means we are trying to embed basically our solid materials that we're looking at in this kind of noble gases. This is the best way just to get the best hydrostatic conditions that we have. And this is in the center here of the pressure chamber that I was explaining you, but you can also get your samples made out from liquids or from gases, like the example that I've shown you also 3 days before, where you have a densified gas mixture of helium plus oxygen, and if you just compress it, then you get the oxygen getting crystallized out in a liquid helium here. So you have exactly the situation that you like. A single crystal of oxygen, solid oxygen, being embedded in a fluid that acts hydrostatically and then gives you the pressure distribution in a very in a way that there is no gradients existing. So, but if you go now to really high pressures, and we are talking pressures about several million atmospheres, then even your diamonds, they start deforming. So I was not telling you that if you really compress a lot your diamonds, then these diamonds are just materials. They also suffer under these big loads. So you start having elastic but also plastic deformation. And basically, in the very first beginning of getting very high pressures, the people were just crushing diamonds in a series. So they were getting pretty expensive experiments because, I mean, crushing a diamond, a pair of diamonds, I don't know how much you pay for a pair of diamonds, but I have at least to pay 1,500 to 2,000 euro or something like this. 5,000. Ah, okay, but you have this in Siberian diamonds. I mean, you sit at the source. It's expensive, basically. You should use them. You should use them, but at least you take care that it's not getting too expensive. And I'm going to show you in my last chapter the experiment. You will see we have crushed all of our diamonds. There were 6 of them we have just destroyed. But usually you try to avoid it because, especially at the corners, Like here, you see there is a lot of strain is evolving, and that makes your diamond just to break it if you're not careful enough. So one thing to overcome this is just to round the tip. But that's something that has been used now the last 10 years already, or maybe even 15 years, what we call a so-called beveled angle. That means you see here there's some extra facets here. These are the so-called bevel facets here, which is a modification just to make it more round, because your tip then, if it bends off, it has not these angles here, and it's flattening out in the regime of these megabug pressures. The other invention that has been made, and was a very good one, it's also about 15 years, maybe even already, yeah, it's about this time, has been done by Reini Böhler, who is now in US, and he was previously in Mainz, and he designed together with a Belgian company which is producing these diamond anvils some new shape to give a support for the diamond through the seat underneath. And this is very helpful. It's like a simple construction, like a bridge. If you think a bridge, it's also not collapsing because you have this support here on different parts of your architecture. And so you do the same here, basically. You use here the diamonds with these conical faces to sit on the support underneath. And in this way, you can really get a better compaction even of your anvil, and the deformation is a little bit more reduced. So it is a good development that has been extensively used in the past few years, routinely, just for going to these multi-megabar pressures, basically. Nevertheless, the diamond still has to be of a certain thickness. And diamond has a pretty high density, so what happens is of course all the electromagnetic signals that you send in, they get reduced, so absorbed basically by the material. So it's not a surprise that sometimes you end up, when looking through the diamonds, that you only have 10% of your signal left over. It's a pity, because I mean you're losing 90% of your signal. Nowadays we can overcome this a little bit, especially for X-ray radiation. We can tune the energy, getting harder energies, shorter wavelengths, then it's getting better. But for some of the methods, like spectroscopic methods, you want to have the whole range of different wavelengths. You have maybe for the short wavelengths a problem of high absorption. And so one of the things to overcome this is to make the thickness smaller, and the idea was here just to make a so-called perforation. That means you see, nowadays made with some lasers, you just burn away some material here, as you can see in the cross-section, and you left over just a thin layer of diamond, which is thick enough just to support the sample chamber and not to break, but then you reduce dramatically the absorption of this material. So it's the so-called perforated diamond anvil, and you can see it here. Then with this, it's easier just to get even for some methods like X-rays, really good signal measured even where you have got this dependency on the wavelengths here. Something that is pretty new just in the past few years is to think about how you can peak up your pressure. And basically what you have seen on the diamond was these diamonds and a flat face. That was the culet face, and then maybe these bevels, which I just explained, that were to round the tip. But the culet face is a simple flat face. And some people had the idea, why not giving inside of this top face some additional structure so that you can go to even higher pressures on a very small area. So they have used focused ion beam technique, which is now something very easy to use and to adapt, just to etch away basically some structure and make this kind of structures that you see here, with a top part here, which is looking in a cross section basically like having an anvil sitting on an anvil basically. So you have got a kind of a double stage system. You will see proper double stage system anyway, and with this kind of so-called toroidal anvils, because you leave out this kind of toroidal excavations here, it is really better just to go in the central part to get to higher pressures, and in this case to reduce the strain that you produce on your anvil. So this is a newest technique that has been successfully implemented, but of course these anvils are expensive, because either you can make it yourself or it's getting really pretty expensive here. And the other alternative is to use some really second anvils that you mount on top. And this is related to a very famous experiment that Leonid Dubrovinsky in Bayreuth has made, where he achieved the highest pressure with the diamond anvil cell so far. You remember I was telling you 700 GPa, that's the world record. That has been done exactly with this here. So what he has used here is, you see here the blue hemisphere. This is another polycrystalline diamond, a small one, that he just put in the center of the orange anvil, lower anvil, on the other side as well. And you have basically between your two anvils here these two extra very small anvils, which are only a few tens of microns in size, because you don't have much more space here in the center of your diamond anvil cell. And in this case, the sample is just this red particle here. That's the sample that has been used for this experiment. So it's very tricky to play around with this. Other people, like colleagues in Japan, have started again to use the FIP technique and just to cut out a second micro anvil that is sitting on top of the face. So what you see here is basically a micro anvil that is exactly this shape here. And this is from Takehiko Yagi. When he was in Vienna, we just were working on this project here. I found some other people that use some extra micro anvils. They put extra here, but this one is really grown from the same material, so it's a direct contact. This is just really used by FIP just to make these micro anvils here, which are acting as this second stage anvils and give you even much higher much higher pressures here. And this was one of the first experiments that they have done. Here you see micro anvils isolated with a platinum sample in between, and again a micro anvil. Everything here, what you see here, is just 20-25 microns, so it's very small, and they place this on the top of their anvil, and we will see this later again when I will show you the microbeam techniques. You see here basically just from the center there is the platinum signal, but 1 micron left, 2 microns left, it's changing the position in the bracket. That means you can get really on a few microns a gradient of the pressure, which you can expect because it's only a few microns off at the center to the left or to the right. Then you change, of course, the pressure conditions. That means we are getting into a regime which is really using very small samples and very small beams. But this is the only chance to get to very high pressures. No other way to do it. So here's again one of these of the exposure that has been used to this, but we will see it later anyway once more, so I can explain it later again. And just sticking with the new materials on the diamond anvil cell and complete this. This is also something that has been done in the past few years. It's using, instead of using single crystal diamonds, the idea was to use a nano polycrystalline diamond, because the single crystal has the big disadvantage, and Jelena can confirm this. Sometimes if your anvil is in the position of a Bragg peak, it diffracts away a lot of your primary beam, and that means you lose this intensity basically, and you have outliers in your statistics. And something to overcome this is using a polycrystalline material, and the polycrystalline material always diffracts in a constant way because some particles are always in a position of diffracting. And the big disadvantage is you get these nasty rings. So it's like any other powder diffractogram that you make. And you see here the big rings, 3 rings from the anvil, and then here the spots. This is from the sample. But you don't have this problem with the statistics. This is working, but I have to say sometimes you lose too many spots sitting on the rings, and you are anyway happy in high pressure diffraction if you really can get what you get, because so much is constrained by the limited space and by the limited access. So that it's a little bit difficult to say if it's really the advantage worth spending the money for this material. So here another few of these images, what we have done with these nanopolycrystalline diamonds in my lab, using a conventional instrument with a conventional microsource, but having then the reconstructed reciprocal space as collected from a Pilatus detector. So, but this is just the materials I was showing you, the anvil materials, that's getting better, but there are also a lot of new changes, for instance, with using split gaskets for some special measurements that you can use, or even with getting the diamond anvil cell itself improved. And one of these improvements, which I want to show you, because I'll show you also results later, is just not using simple screws or the gas membrane for pushing together the 2 anvils, but using, in this case, piezo actuators, which just make the small changes in the size that is enough just to push together your 2 anvils. Because the anvil anyway on the tip is very small, and the force outside needs not to be that big in order to get really the proper multiplication factor for increasing the pressure in this way. So this is an easy way to control it, and we will see later you can be dynamically, basically. So you see here, this is also a picture from the experiment I will show later. You have this diamond anvil cell here, where it's possible to do ramp compression. You can change gradually the pressure in a given time, and you can control this as you just increase the piezo, the current, and then you get the constant change of your pressure in time. And if you then do time-dependent measurement, you get the dependency on time. So it's getting into the field of time-resolved crystallography, basically. And the other important thing is, of course, microbeams. Microbeams, because we need, no, this is about the detectors, but why? Yeah, for the detectors, I just wanted to say that the detectors is also something that is important to change. So we have seen silicon, we have got silicon pixel detectors that improved a lot to shorten the detection time, which is necessary if you want to do the time resolved or time optimized measurements. And this is especially important if you have high temperatures and everything is faster in terms that you can overcome kinetics easier. Then it is important that you really have these fast detectors just to see what is going on, if there are changes or not. And you see here, there are some measurements done in the lab at pretty moderate temperature conditions, but in this case, it was necessary just to see very weak, very faint reflections, superstructure reflections, which are coming out from only a small change, a small displacement of oxygen atoms. Yeah. No. Yeah.
On the pixel detectors, well, with radiation damage with that sort of
For the silicon pixel detectors, I've heard of this, that it's increasing with this, but this is just synchrotron radiation. So I mean, you have to ask, of course, the people which are sitting at the beam lines if they see this problem. I mean, I can only say from my Pilatus at home, which I run at 0.7, I don't have this problem, certainly not. But the lower. Yeah, but yeah, well, the other way is, of course, to get to cadmium telluride. That's the newest technique, basically, and that's ending. Basically, that's going up to where the newest detectors are used, basically. And you see, I've just taken this one image to show you that's the newest technique that we have. It's replacing the sensor material silicon by the cadmium telluride. Of course, cadmium telluride is more expensive, but the quantum efficiency is, especially for the higher energies, is much better than it was for the silicon, and it has certainly some advantages. I guess what I've heard is the current detectors have a problem with dead time in comparison to silicon, but in general they are much quicker, so that means it is a big advantage here. The microbeam is the other thing. That means making the beam smaller. We are not talking about microbeams anymore, we are talking about nanobeams. I mean, we have really small beams which are necessary, as I have shown you in this one example. And again, what is the same example I've shown you before. What you see here is a 1 micron beam that was necessary, and that spring 8 with this high brilliance, it's sufficient to make a 1 second exposure in a diamond anvil cell, which is what you will see here at 240 GPa. So it means pretty small sample, very high pressure, and in comparison, a rather short exposure time. Of course, you can see that the signal to noise ratio is not as beautiful as you want to have it, but you really want to be quick, because sometimes you don't have the time, because I mean, if you change pressure, temperature, then things can happen to change, and this happens sometimes even at high pressures pretty fast. So you see here again, this is what I was showing you before. You see here at the center here, and then displace the beam by 1 micron, by 2 microns, 3 microns, and you see the one peak of the platinum here. It's changing immediately. After 2 or 3 microns, it's going to much lower to theta values. That means you can see that there is a gradient of the pressure from the center just in a micrometer step, basically. And that's necessary if you really want to do this kind of extreme measurements with very small samples using this second stage anvils, because otherwise you are measuring just an average of everything, and you never know really what is your peak pressure, what is the real conditions at the center that you have here. So you need to do this kind of gradients. On the other hand, the smaller the beam you make, and especially if you don't have a single crystal, you have the problem that you catch not as many crystals anymore. That means on the pathway through a powdered sample, it may be that your beam, your small beam, is hitting only a finite number of crystallites. So we come into this regime that we can deal with these individual crystallites really like single crystals, and saying, okay, let's have 10 crystals which are diffracting, and then we can do this kind of a treatment of the data using 10 single crystals and having 10 orientation matrices, and then working like what we are used from single crystal diffraction. And that brings us to so-called multi-grain crystallography, which is nothing else than a combination of using single crystal techniques, but extending the numbers of single crystals that you use. So you can really give to all the spots that you have here on the debye ring, you can basically give them a name. You can label them, say this is crystal 1, this is crystal 2, this is crystal 3, such as I have shown here, basically. So the dynamic compression is the most recent field, and this is something I can basically not show you some results because it's just something that is going on, starting with very simple shock physics, but nowadays using these high energy lasers, the pulsed lasers that are producing shock waves. So I give you just a short idea about what's going on. We have heard about XFEL, and that this is a technique even in extreme condition research in the future. You see here a picture where the XFEL in Hamburg was just about 2 years ago, 2.5 years, when they were just to finish the tunnel basically, and I had the last opportunity to access this tunnel. So that's me, what you see here. It's 2 kilometer straight line. Nowadays there is the accelerator already, and all the magnets and everything is inside, and it's built already, so you cannot exit anymore because it's already under operation. And basically the big advantage is that you use the structured feature of these and the bunch structure that is provided by the electron field. So you see here, you have got this kind of bunch trains of very short X-ray pulses that are separated by some intervals, and this kind of structure of the beam with this time resolution that can be used even to do up to femtosecond investigations. And for the first high pressure and extreme conditions experiments, it was easy to combine this with a laser, a pulsed laser that gives you a shock wave through your sample. And what you see here is basically a shock wave running from this side to the right. You see the front of the shock wave propagating here in fractions of a nanoseconds, and you can really image this by the contrast, density contrast, what is given here. But you can also do, of course, the diffraction if necessary. And there are plans for the future in Hamburg that they will have even a station where you can use a diamond anvil cell of pre-compress your sample and then doing by this laser which goes through the diamond anvil, basically then making this kind of these shock waves, and then finding out by applying the X-ray beam from the XFEL just to get its time resolved, basically the changes of the structure under these conditions here. So what is the aim? Basically just to go to even more extreme conditions. And you see, we change now, we go away from gigapascal, which we are very familiar. We are talking about 1,000 to 2,000 gigapascal, so we can call them already terapascal, basically, because we have now a factor of 1,000 to be added. And in these conditions, for instance, we are expecting that even diamond will undergo a phase transition to some other compound. So that's a little bit, not so many real data. Now I'm going back to my 2 examples that I want to show you. And the first is, what did I have? No, the first one is about carbonates. And for those which are not so familiar with the calcium carbonate, I have plotted here the phase diagram, and what you see, it is pretty rich in polymorphs. So you see the natural one that everybody knows because it's building up mountains, and is the calcite. That's the number 1 here. But then you see there are also a lot of high temperature, high pressure, and even high pressure, high temperature polymorphs that are known. And at the same time, you see here the mantle geotherm. That's the line of, if you go into interior of the Earth, basically, where you can expect the pressure, temperature conditions. And the other extreme is if subduction takes place, you have cold material going down, the pressure is high, but the temperature is low. That means, so this is the range, basically, where we are talking about if we go into the Earth. But nevertheless, I will focus just on these very low pressure and very low pressure temperature conditions, where you may think everything must be known because it's easy to access it there. So what you see here is the first high pressure phase is the phase number 2, which is changing from trigonal to monoclinic, and this is well known. This is a well-known phase transition that even has been observed by Percy Bridgman. So he was really a long time ago, because it's easy to access and the samples were big enough at this time. And then it's followed by a field that is called calcite 3. And this calcite 3 was ever something puzzling, because people said, there's a monoclinic one, there's a triclinic one, there's something not solved. So finally we ended up in having something like a calcite 3b, because we found an alternative. So still a lot of questions that were open. So we have done now in situ measurements, both with X-ray diffraction, but also with vibrational spectroscopy. And what you see here is basically just a simple sequence of Raman spectra that are going from the phase 1 across the phase boundaries of phase 2 to this field of whatever it's there, 3, 3b, whatever. And if you look here, you basically see here the first spectrum, that's the typical one, it's boring. Then the next two are phase 2, the monoclinic ones, this is also well known, and then the rest is everything related to phase 3. But you see there is a difference, because small features are changing. It's not looking that obvious, but they are changing. And we have the phase 3b up to about here, 3.4 GPa, and then it's followed by the phase 3. So we can see this here. There are some extra lines coming up in some features. So obviously two structures which are very similar, and only a small change, which is nothing else than it's not a kind of modulation. It's a superstructure. That's it, the word. That is occurring here in this triclinic phase, basically, that makes the change basically here. If you look at the structures, you can see from phase 1 to 2 to 3, it is from the trigonal structure is then distorting into monoclinic, and then the next step is to get inclined the CO3 groups, and once they're inclining, it's getting triclinic. So these are the first 3 steps, which are very obvious, and this very simple displacive mechanism that you can see here. And if we collected all the data points and put them together, we found basically something like a phase diagram with having 1, 2 established where it is, and in the field of phase 3, we have found this small triangle here, that this is the phase, that is the area where phase 3b is existing. So it only existed basically if the temperature were not too high. And a lot of people haven't seen it because they have just a little bit higher temperature, or the pressure step was too quick and they have never ever seen it. So phase 3 has also been reported, but phase 3b was reported later. That's why it got the B, because it was reported later. What you see, all these phases here are different in the volume, so that means they are first order phase transitions that we have basically that we have seen here. So what we have done now was using this technique I was explaining you on Stanford synchrotron radiation light source. We have done one experiment here, and what you see here is basically now the sequence of the ramp compression starting at 1.09 GPa, going up to 2.3 GPa. So it is related to this first transition from 1 to 2. And you see here very fine lines. Each of them is 1 diffractogram. So it is collected from a Pilatus. That's why we had this detector module gaps, because we have got the Pilatus with the 3 modules. So we could not record here, basically, but we have collected all these spectra. So it's about 170 spectra or something like this that you see here in this sequence. And you don't see that much. You just see there is a reference material for the pressure calibration, which in this case was the copper. You see the nasty gasket lines as well. And then, especially in these areas which are here, basically you see, if you go to this phase transition boundary in this case between 1.5 to 1.7, you see really that it's changing from the trigonal in a time interval and then finally being the monoclinic one. So that's what we would have expected. But the interesting part is we have the impression, as this is a sequence about 20 seconds, because each diffractogram is recorded 1 second, we had 20 seconds, this coexistence of this both while it's leaning over basically, like in a very simple way. You see it here, very nice. This one peak of the intensity is then splitting into two, and you can see it's only half the intensity roughly, the two components have. So it makes sense. It was a nice way. So going up to higher pressures, 2.4 to 3.5, that should cover now the next transitions. And you see again here, obviously something is changing here again, but then if you look up into detail here, again, you see this is now changing from phase 2 to phase 3, and we have a field of coexistence of phase 3 and 3b here. So it's basically something we can also understand. We were pretty satisfied and said, okay, that's fine, and then continued this to even higher pressures. Then we found, very interestingly here, basically if we change the compression rate, then this field of the coexistence is narrowing up, and it's pushing these equilibrium boundary conditions around. So you will see in a second, when I'm showing this later, after this image here, that you will get new transition points, basically. But at 4.7 GPa, something additional happened. And that was the surprise that we were not expecting, because we have seen, if you look up here from this image, it's just plotted this way. Again, there is some non-linear evolution here and some changes, basically, which indicate that there is another phase that we are terming the calcite 3C. And what we see basically here is that these transition lines that have been reported to be here, they shifted up to here, and a new phase transition has been now seen here at 4.7 to come to the phase 3C. So that means if we do this dynamically, we see that we can push around these phase transitions, even though they are very simple transitions, because it's just displacive. It's not something that we are changing a lot, the coordination numbers or something like this. We have to be very careful with the kind of how much pressure we change basically in time. So we were investigating this also by the Raman, and then we have seen basically these changes here again, and in one direction we didn't see anything, and in the other direction of these oriented crystals it was very massive at this 4.8 that we see changes in the Raman spectrum. So it's very obvious that basically this similar structure in one direction but not in the other direction, where we can see basically these new features coming up or disappearing basically. So plotting all these Raman spectra that we have measured together, we can be pretty convinced that we have now this phase 3, because it's different from the phase 3 and the phase 3b and 3. This difference has been established anyway, including the X-ray diffraction. That means it is just an example showing you that the polymorphism, even in ranges which is not that extreme, can be very surprising sometimes, and this is the one example I wanted to show here. The last example I'm showing is about the CO2. For the CO2, I think I don't need to explain you in detail that this is some well-known gas that is always under discussion, and we'd like to store it if possible, because we have too much on our globus. Basically, there is a big discussion about how can we get rid of this CO2. CO2 sequestration is a big matter. On the other hand, we know that there is a permanent source of CO2 coming up from recycling through subduction zone processes and so on. So that means it is not well balanced at the moment. And it's not only the surface near CO2 circle, but it's also including the deep CO2 circle. That plays an important role because a lot of sediments are subducted through the subduction zone into the depths of the Earth, and this goes up well down to the core mantle boundary. So the question was, what is about the CO2? And you will see in a second, there was the general finding was established that the CO2 is not stable at mantle conditions. So that was what we were faced with. And basically, I can tell you we were not really investigating CO2, but we used CO2 as a reacting agent in our experiments and wanted to react it with something else. And then we found out that CO2 itself is stable. But you'll see this in a second later. So here is a PT plot, again with the mantle geotherm and the very cold slab here. So you see the upper mantle transitions on lower mantle up to 130 GPa. That means 135 is the core, where the core starts. So we just have a PT space here relevant to the mantle, basically. And the normal temperature distribution is just following this gradient just down. And if you just go along the subduction zone, you see it is much colder, but the pressure is of course given by the depths here. So if we keep these two lines in mind between the normal geotherm and a cold subduction zone, then this is the area that we have to look at basically when we are talking about our CO2. And all the knowledge that has been obtained so far is plotted here in this phase diagram, which is, as you can see again, a lot of polymorphism that can be seen. And it starts with the simple solid that you know as dry ice, which is even extended to pressures up to 10 GPa here, which is a simple structure where the CO2 molecule is kept in its shape, like what we know that CO2 should look like. On the other hand, it still is molecular CO2, but with a different arrangement that is well known for this so-called CO2-4, which goes up to about 40-50 GPa. So pretty high pressure already. And it touches also this regime of the cold subduction zone. And above this here, basically, we can expect CO2 to be liquid. Above this border that is going down here, you'll see CO2-5 is changing now. It's going away from a molecular system. Now we have a fourfold coordination in the tetrahedron, similar to what we know from silica. So it is a structure that is pretty the same as the mineral cristobalite, because it is silica, where in the fourfold coordination, you just replace the silicon by the carbon atom, and you end up in the same structure here. So that means basically here is a trend line here, where we have got the molecular phases, while on the other side here we have got these polymerized or extended phases that involve the coordination change. So that means we can expect for all these lower mantle conditions to have carbon no more in the way that we know it to be coordinated, either twofold coordinated in CO2 or threefold coordinated in carbonates, but it must be fourfold coordinated. Is it okay for time? I have no idea. I have a few slides. This is the last example. Okay. So, and what is interesting is that a lot of investigations have been made showing that the CO2 is breaking down. So especially for the people working on diamond formation and mantle conditions, they have reported, partially pretty shifted, but they have reported breakdown lines like what you see here. That was well established, and in principle, you can say that that most of the people have said in this area here, above this here, there is no CO2 existing because it's breaking down to diamond, having a C, a disproportionation to carbon as a diamond, and then having to release the oxygen, which is in the Earth's mantle, known to oxidize the iron components. So that was the model that has been established. And we have done these experiments, and don't get shocked, that's a typical way of doing a laser heating experiment. Here is your diamond anvil cell in the center, and what you see here is a lot of laser heating devices and objectives for measuring the pressure and so on. So it's very, very tricky to touch something here. But we have done now this experiment using now magnesium carbonate as the infrared absorber for our laser. We use the CO2 laser basically. Then we have loaded the liquid CO2 inside the pressure chamber. And then, of course, we need also some pressure reference because you never know exactly which pressure you are. And we have used a beveled anvil. Like I explained to you, if you go to this above 1 megabar, you need to have these beveled angles. This is exactly what you see here. And the sample basically finally looked like this here. This is the solid CO2 here. It looks pretty, yeah, unspectacular, but that's it basically. And the loading itself was done by liquefying CO2 under 32 bars and cooling it down to something, a temperature similar to what we have here outside. And that makes CO2 liquid if you increase the pressure. And that gives the easy possibility just to load it inside your cell. And then the fun could start with placing this cell here in the central part. You see here the detector, that means the beam is coming from this side, and then you get diffraction basically here. And all the rest around is just for the laser and for the temperature determination and everything else, which makes it, of course, more complicated here. So, in addition, after the experiment, we have done Raman measurements as well on the cell, because we have taken the cell from the ESRF with us, and then went to Firenze in the laboratory of nonlinear spectroscopy, where the colleagues there made all the measurements of the results after laser heating there. So, and what were the results basically? So, what we were surprised is that basically first, there was not a surprise, is you see, as you increase the pressure continuously, you amorphize your CO2. That's common, pretty common. So that means we knew we have an amorphized CO2 at this point, and then we know if you start it, then something, we were trying to react it with this magnesium carbonate, but this didn't take place. But what happened is that the Bragg peaks of the CO2-5 showed up as we started laser heating. So that means we must have probably have a stable phase there, and it was, as we found out later, just CO2-5 that was already known basically. The only advantage that we had is we used this magnesium carbonate, and the magnesium carbonate was a pretty good absorber for the CO2 laser, and the normal CO2 is no more absorbing that much once it is in this regime of having transformed into this extended phase, because then the frequency, the resonance frequencies are shifting, and then the CO bond is no more in as good as it would have been for a normal carbonate, and the magnesium carbonate still is. So that means we were just lucky to have the magnesium carbonate as the absorber, and basically then having pretty high temperatures, about almost 3000 Kelvin, that enabled us to see the recrystallization. So that means we were seeing basically the CO2 coming up again, although it was said it should not exist. And so we could measure even compressibilities, equation of state. I don't go too much into details. You see our data points were fitting perfectly with the CO2-5 that was known at much lower pressures, because we were at really high pressures basically in this case here. And even going back after the experiment at home and measuring the Raman spectra, and the modes were exactly what you were expecting from what has been reported from the other modes in the past. So it means we have seen basically the CO2 just to come again. But the question was, why did all the other people say it's breaking down? And then we did some scanning as well through our pressure chamber, and we recognized we have beta rhenium dioxide. And the rhenium is the material that we use for the gasket. And then it made, we know what happened. We have a simple redox reaction of the hot CO2 with the rhenium metal that was produced in rhenium oxide, and it produced, of course, free oxygen and some carbon, in this case diamond. And all the people have seen in the past basically just this artifact that the hot CO2 in their experiment was eating up basically the gasket material outside. We've repeated the experiment using gold, and the gold is preserving this, and it's stable and it's working perfectly. So with these findings, of course, we have the problem with the implications, because we now hit a lot of people in their theories about the formation of diamonds, because everything that has been published before, now you see it's in our diagram with all these breakdown reactions, it's not breaking down. So it's only breaking down in the experimental setup if you use the rhenium and they do not take care to protect it from the reaction with your hot CO2. If you do it, like our data points, you still have free CO2 here. And it's perfectly stable, which has been reported by the people which have done computational simulations, because they said it should be stable. And only the experimentalists said, no, it's not stable. But now we know it is stable. So in this case, it's one of the few occasions where the computational people are right and the experimental have to say, okay, it is like this, but we can explain it now. So we don't have this breakdown basically here. It is not the mechanism to form these diamonds, but maybe the CO2 is reacting in some way, and that's basically what we can do. I don't go into these details, I think, to save time a little bit. It's just what I have explained to you. It's just written up here again. The only important thing for me, is the geological implication is that the current models of the formation of these super deep diamonds must be modified. Again, I would not say the CO2 is stable there. It probably reacts with the other mineral phases. That's very likely. But at least it's not breaking down on itself. And that's the important message, that what we have found out. We were, of course, lucky to get this published in Nature Communication, because this was really changing all the current established models so far. And basically, that's what I want to say. Thank you. I want to acknowledge first all the people that have been involved in the two examples here, which is the people from Lens, Kamil Jubek and Demetra Schelter, Roberto Bini, then at the SRF, the Beamline scientists, Mohamed Meso and Gaston Gabarino, then from my group, Martin Ende, David Zinger and Thomas Pippinger, then the cooperation with Yongjae Lee and his students for the measurements of the dynamic compression of the carbonates, and then I would also like to thank my Japanese colleagues for the nanopolycrystalline diamond project. And I think I have one more slide, and I hope you will forgive me for this. No, this is just saying, no, that's not the slide. That's just thank you for you all. And the last is that, we should not forget, you have birthday today, right? Yeah, it's right. So happy birthday. So thank you.
Поняли, как опасно корректно ставить эксперименты. Можно разрушить все, что делали до того. Но это неизбежно. Все равно рано или поздно все тайное станет явным.
You showed how the pressure profile moves very quickly.
Yeah.
When in the nanocells.
If you step aside, right.
So how is the pressure measured there?
It's by the equation of state of the platinum which has been established to a certain extent, and then it's an extrapolation in some parts. So it is nothing else than the equation of state has been determined, and then you just go there, and from the lines, from the d-spacing, as the platinum is a simple structure, you can easily calculate the molar volume, and that's a reference for the pressure. That was the reason for using the platinum here, because it was acting as the pressure reference at the same time. It was sample and pressure sensor.
Еще вопросы? Я поняла, что вопрос, да?
Roman, Alexander, and me, we are interested in the first or the second slide, the name of your institute. You mean twice and crystallography, department, mineralogy, and crystallography.
Oh, that's too much. There's one crystallography too much. Really? I did make a mistake? Okay, sorry. That I did not recognize this. Oh, okay. That's okay. It's only one crystallography is enough.
Еще какие-то вопросы? Значит, если нет вопросов, программа такая. Сейчас быстро-быстро одевайтесь. Внизу вас ждет автобус, который должен отвезти вас во внешнюю университетскую столовую, отдельно стоящее здание. Там вы быстро-быстро обедаете, и автобус привозит вас обратно. You now have lunch break. Buses are waiting down to bring you to the separate canteen. Как приедете, так начнем.
Was it too long? I have
No. It's okay.
I have no idea about the time.
It was perfect. It was exactly what I was expecting. So if you want to have a decent lunch, you join everyone, and the bus brings you to normal canteen where you should be served lunch. I stay here just because I have something like 20 unanswered calls, and I want to start answering them, and I'll eat something from now on.
I need not to go to canteen. I would also rather prefer.
It's up to you. I just say that
will,
there are two options. Я могу остаться до конца, или меня не выгонят, если я тут поеду? Ну, я понимаю, я сейчас начну отвечать на непринятые вызовы, после этого.
Is the web?
Wait, I can't hear in two play.
Sorry.
So yeah,
I was wondering if the web was accessible on here.
the web here. I don't know.
World Wide
I
Web,
don't
yeah.
know. Okay, I don't know. How can I take this out here? No.
No, you need to close your talk.
Yeah. But,
It's in Russian, I suppose.
yeah, I cannot read it where to close it. It's maybe here.
How do we come out of Ron's talk?
It's here. And
Next.
what?
Where is your presentation?
Here.
No, but we need to close the talk.
Cool. Sorry.
I cannot read the Russian, you know.
Yes, I know.
Maybe I can read it, but
It's open, it seems to me. I'll check. it.
Ну, как сказать?